Here is the combined summary of the 4 pages. The proposed method, AndroCon, leverages semi-processed GPS data to sense the ambient, recognize human activity, and map indoor spaces with high accuracy. By exploiting the release of Android 7, which provides precise location permissions, the approach accesses semi-processed GPS data to yield highly accurate ambient and human activity sensors. The methodology employs linear discriminant analysis, unscented Kalman filtering, gradient boosting, and random forest-based learning to achieve this. A longitudinal study was conducted, collecting semi-processed GPS measurements over a year using different mobile devices spread across a 40,000 square kilometers geographical region. Data was also collected on flights, cruise ships, and high-altitude locations. A thorough characterization of satellite GPS signals was performed, and cross-correlation analysis was used to extract the best set of features that preserve vital information. The results show that AndroCon can easily identify difficult scenarios, such as being inside a metro, a person waving a hand in front of the mobile device, being in front of a staircase, and the presence of people in the room. This is the most comprehensive study on satellite GPS BASED sensing to date. GPS signals contain various parameters, including pseudorange, signal-to-noise ratio, phase shifts, Doppler shifts, and satellite information, which are essential for receivers to correct their data. The GPS processing pipeline at the receiver involves code and carrier tracking loops, which demodulate and identify incoming GPS signals, enabling the calculation of pseudorange. By tapping into the pipeline, 9 semi-processed GPS parameters can be extracted, including received signal power, carrier phase shift, multipath interference, signal-to-noise ratio, and Doppler shift. Linear discriminant analysis is employed for dimensionality reduction in pattern classification applications, projecting the dataset into a lower dimensional space and enhancing class separability. The unscented Kalman filter is used for noise filtering in nonlinear systems, predicting the future state of a nonlinear system and updating this prediction using incoming noisy measurements. The unscented Kalman filter is employed to estimate the state and covariance of a system, with equations 12-14, defining the prediction and update steps. This filter utilizes sigma points to represent the state and covariance, enabling the computation of the cross-covariance matrix Quart and residual covariance matrix Street. The Kalman gain KT is then calculated, updating the state and covariance. The research leverages semi-processed GPS data, available on Android platforms from Android 7 onwards, to infer the state of motion and environmental context of individuals. This data provides access to 9 GPS parameters, including Doppler shift, carrier phase, signal-to-noise ratio, received signal strength, and multipath interference. The Doppler shift and carrier phase facilitate the differentiation between motion states and environmental contexts, while signal-to-noise ratio and received signal strength are crucial for evaluating GNSS signal quality. Real-world data collection was conducted using 5 Android phones, logging semi-processed GPS data, and supplemented with open-source datasets to ensure robustness. The study highlights the importance of noise filtering techniques to mitigate the effects of ionospheric electron density variations and weather conditions on GPS signals. The collected data was used to simulate diverse user activities and environments, including open grounds, indoors, and different weather conditions. The research then utilizes linear discriminant analysis for feature selection and evaluates 6 machine learning algorithms for classification. The evaluation setup involves a dataset collected in various locations, involving 20 volunteers, and is split into 80% for training and 20% for testing. The results show that combining parameters significantly improves accuracy, with random forest and gradient boosting models achieving over 90% accuracy for all settings. The paper concludes by summarizing the performance metrics for each setting, including accuracy, sensitivity, and specificity. Here is a combined summary of pages 912. The authors present the results of their ambient classifier models, achieving high accuracy in identifying different environments such as flight, indoor, metro, open ground, and outdoor crowded spaces. The gradient boosting (GB) and random forest (RF) models outperform others, with GB achieving an accuracy of 99.8% and RF achieving an accuracy of 99.5%. The feature importance evaluation reveals that AGC has the highest importance score of 0.78 in ambient classification. In human activity recognition, HAR, the authors utilize Doppler shifts to distinguish between dynamic activities such as walking, running, or traveling in a vehicle, and classify static activities into 4 classes: sitting, standing, lying down, and hand-waving. They employ a combination of features, including speed, acceleration, and GPS parameters, to classify these activities. The results of the HAR experiments are presented in confusion matrices, showing the accuracy of each activity for each semi-processed GPS parameter. The authors find that AGC achieves the highest accuracy of 77.2%, while ADRNG performs the worst with a high misclassification rate of 72.6%. The performance of various machine learning models for activity classification is evaluated using a dataset with semi-processed GPS parameters. The random forest (RF) model achieves the highest accuracy for handwaving, lying down, sitting, and standing. The gradient boosting (GB) model also performs well, outperforming the k-nearest neighbors (KNN) and naive Bayes (NB) models. The support vector machine (SVM) model performs poorly. The robustness of the method is assessed by conducting experiments with varying environmental conditions, satellite vehicle ID, SVID, density, and test train split. The results show that the method is robust to changes in these parameters, with the accuracy remaining above 91.5% for ambient recognition and 83% for activity classification. The feature importance test for human activity recognition reveals that the acceleration, AGC, and state features are the most important for predicting the activity. The research presents AndroCon, a novel approach utilizing semi-processed GPS data to create indoor floor maps, overcoming GPS signal limitations in indoor environments. The authors investigate variability in accuracy across different phones and environmental conditions, employing a UKF and LDA approach to mitigate noisy readings and handle varying ambient conditions. To create the indoor floor map, GPS RSS patterns are studied in a large indoor area, generating a heat map depicting relative GPS RSS levels. 2 access points outside the site simulated GPS setting, showing a high correlation between scaled data and real-world GPS signal intensity. A trajectory creation methodology is proposed, relying on multiple users to collect semi-processed GPS parameters, human activity recognition, HAR, fingerprints, and trajectory information. A trajectory alignment algorithm is employed to merge results and identify landmarks, such as pathways, stairs, elevators, rooms, and obstructions, using a transformation matrix to adjust curvilinear paths, translation, and rotation. The approach is evaluated, achieving a maximum error of 4.10 meters for the graph discrepancy metric and 3.41 meters for the shape discrepancy metric. Landmark detection accuracy is assessed using a GPS BASED HAR system, achieving an average accuracy of 90.15% with a random forest classifier. AndroCon recognizes human activity, senses ambient conditions, and constructs indoor floor maps without relying on GPS coordinates, Wi-Fi signals, or camera data. Extensive experiments demonstrate high accuracy in recognizing human activity and ambient conditions, with a range of 99.5% in controlled conditions to 87% in uncontrolled conditions. The approach also shows the ability to construct indoor floor maps with a maximum error margin of 4.1 meters and classify points of interest with an accuracy of approximately 90.15%. This section presents a comprehensive overview of indoor floor mapping approaches, comparing methods and techniques through a detailed table. The table highlights the use of different sensors, such as IMU, GPS, Wi-Fi, and LiDAR, as well as various methods, including user trajectory alignment, link node approaches, and fusion of multiple sensors. A thorough literature review follows, covering topics such as location-based services, human activity recognition, and dimensionality reduction. Machine learning algorithms, including support vector machines, random forests, and neural networks, are discussed for activity recognition and classification. The importance of data scaling methods, data fusion, and sensor selection for improving human activity recognition accuracy is also emphasized. Challenges and limitations of existing approaches are addressed, including issues related to GPS signal strength, multipath effects, and ionospheric delays. The role of crowdsourcing in indoor mapping is explored, highlighting its potential in constructing and refining indoor maps. Techniques for integrating multiple sources of data, including GPS, Wi-Fi, and inertial measurements, are discussed to achieve more accurate and robust indoor mapping. The review concludes by emphasizing the need for further research in indoor floor mapping, particularly in addressing scalability, robustness, and generalizability challenges. The authors highlight the importance of developing sophisticated algorithms and techniques to handle the complexities of real-world indoor environments. Key challenges and limitations are identified, including the need for improved sensor selection, data fusion methods, and robustness against environmental factors. The literature review provides a foundation for understanding the current state of indoor floor mapping and highlights the need for continued research in this field.